From the beautiful South Studios of Way Happy, this is Mr. Meyer and 11.6 binomial distributions. Now, what we're going to do is we are going to FOIL out some stuff, right? But if that exponent gets really big, all of a sudden life gets pretty miserable. And there's this guy named Pascal who noticed something. He FOILed out a bunch of stuff. If you look right here, he did x plus y to the 0 and he got that. And then he did x plus y to the first and he got that. And he did x plus y squared and he got that, right? And so he kept doing this and doing this over and over again because that's what math people do. And then he said, I wonder if there's any pattern there. And he did. He noticed he had a 1 here, he had a 1 here and here. Then he had a 1, 2, 1. Then he had this 1, 3, 3, 1. And he was like, wow, this is neat, right? And he pulled the numbers out into what we call Pascal's triangle. And then he didn't stop there. He was like, I wonder if there would be any way for me to figure out what the next row would be, and the next row, and the next row, and the next row, because he was just having way too much fun. And he noticed that these two add up to that one, and these two add up to that one. So as he continued to do this, he's like, all right, looks like they always start with a 1. And then if I add these two, I get 4. If I add these two, I get 6. And if I add these two, I get 4. And then I end with a 1. And he noticed that this worked. And so then he felt super excited. And he could continue his triangle forever and ever and ever. And therefore, he felt like we didn't need to FOIL anymore. He found maybe a better way. The other thing you might notice too is look at what he had in parentheses here. The front thing started off with the exponent, but then it went down 1 every time until it disappeared. And the back parentheses disappeared, but then they started to increase in power by 1 until they got to the maximum. And all of that created is Pascal's triangle and how to FOIL or expand a binomial out. It only works with binomials, 2 terms. Then along came the binomial theorem, which said, hey, I really wish I could find a way to, instead of having to add all these numbers together, I wonder if there's another way. Turns out it's combinations. You can see row 3 right there. I know it looks like row 4, but it's actually row 3 because we start with row 0 to the 0 power. Row 4 has all those different combinations that make up those numbers. So depending on what row you are, that's how you create those numbers. And the binomial theorem says, boom, let's just do that. You're going to create those numbers and then do the front of the parentheses to the highest power and keep going down, the back of the parentheses to the lowest power, and then keep going up, and you will be able to expand. And so let me quit talking and do some math, right? So here you go. Let me expand this. Now you could write that out 5 times, right? You could write it out 5 times, or you could do the binomial theorem. Now I do the binomial theorem a little different. They do it going across. I do it going down. Just easier and less messy. So here we go. It starts off with NC0. So we're going to start off with 5C0. We have to go 5C1, 5C2, 5C3, 5C4, and 5C5. Now again, those you could have gotten either with your calculator or Pascal's triangle to row 5. So here's his triangle to row 5. I know this is 1, 4, 6, 4, 1. Here comes the next one. 1, 5 is the one I need. 10, 10, 5, 1. 1, 5, 10, 10, 5, 1 on Pascal's triangle. So this is really 1, 5, 10, 10, 5, and 1. Now, what else do you have to do for this thing to work? You either get those numbers off of Pascal's triangle or using combinations, up to you. After you've done that, you've taken care of kind of the power. You want to go to the front of the parentheses, whatever it is. You're going to do that to the 5th power or whatever power you have. And you're going to keep powering down by 1 until you get to a to the whatever you had to the 0 power, which nobody ever writes, right? A to the 0 is 1, it disappears. Then you do the back of the parentheses. In this case, we have B, and you do B to the 0, and you go all the way up. So look what I've done. I've gone the front of the parentheses down, and then I've gone the back of the parentheses up, and lo and behold, you will be done. So what do you get for each term here? I get a 1 a to the 5th, so a to the 5th. I get a 5 a to the 4th b. I get a 10 a cubed b squared. I get a 10 a squared b cubed. I get a 5 a b to the 4th, and I get a b to the 5th. And if you FOIL this out and make 0 mistakes, you will get your answer. A to the 5th plus 5 a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the fifth. Holy smokes, there's your answer. Now imagine foiling. You would be doing that and you'd be combining like terms, and oh my gosh, you could run into a chance for a mistake. And so be super careful, right? Be careful about those parentheses and what's getting power. So let me show you the next one just to make sure. This is to the third power, so I need the third row. 1, 3, 3, 1, or 3C0, 3C1, 3C2, 3C3. We'll get you those numbers. Then again, I'm going to use colors. The front of the parentheses is a little trickier this time. 2x cubed, 2x squared, 2x to the first, and 2x to the 0. That one's going to disappear. The back of the parentheses, this is really tricky, by the way. If it's negative, it's not, so I'm good. Y to the 0, y to the 1, y to the 2, and y to the 3. And now look, all those things are multiplied together, so make sure you multiply them together. I don't want to see any adding or subtracting in there. If it's negative, pull the negative out front. All right, so what do I get? 2 cubed is 8, so this is 8x cubed. This is 3 times 4, which is 12. So that's 12x squared y. Then this is 3 times 2 to the first. That's going to be 6xy squared. And last but not least, 1, y cubed. And so there we have it. This answer would be 8x cubed plus 12x squared y plus 6xy squared plus y cubed. And there it is, completely foiled out perfectly, and a lot less mistakes than combining like terms or drawing the box or whatever. There you go. Let me have you try one, and we'll be right back. Nice work on that one. All right. Now let's talk about binomial probability. Now, this is one of the things that I always thought was really neat. This is binomial probability happens if you're going to do n trials and you want to know how many ways that someone's going to be successful or something. Now, the bad news about binomials, got to have two outcomes. Like it can only be like, yeah, they made it, or no, they didn't, or you passed the test or you didn't, or you got the problem right or you got the problem wrong. There can only be two options if you're going to do this binomial probability. And you could do this other ways. This is just a neat thing about the binomial theorem. And you can see right here in the probability that this is really the binomial theorem. And that's where it came from. And so it's nothing too crazy different. So let me just show you how you actually use it. So here's example 2. It says Gina usually makes half of her free throws. So she's 50-50, right? Today she tries 3 free throws. What's the probability that she will make exactly 1? Now you could totally do this tree diagram way, right? Like I said, I always did a tree diagram when I was doing statistics. So I mean, here's the first option. She's either going to make it or she's going to miss. Okay, that's probably not good. It's either going to be good or bad. Let's go good or bad. And then that was her first shot. Then her second shot is either going to be good or bad. And then her third shot is either going to be good or bad. And so this would be the tree diagram that I would have made for every single outcome of Jean's shots. And so you can see right here, that's a lot of work, but it does in fact work. In fact, she is 50-50 on both of them too, right? Making it or missing it, making it or missing it, making it or missing it. And so the fact that she would make it good, that's 50%, 50%, 50, sorry, 1/2 times 1/2 times 1/2. That is 1/8 of a chance that happens. Or good, bad was 1/8 of a chance. And what is this? Good, bad, good. That's 1/8. And this one, I'm starting to get the hang of it. These are all 1/8 chance. In fact, they're all equally likely outcomes with her 50-50 shot. And then I could answer the question. I could say, all right, how many of these is exactly one way that she made one good one? So that would be, she can't go good. So this is all gone. So she can only go good, bad, bad. I guess that's the only one out of the top branch. Down here, she could have gone bad, good, bad, or she could have gone bad, bad, good. So I can then say, well, she either did this outcome or this one or this one. And remember, if you say or, that means add them together. So it's going to be 3/8 of a chance. So that's the answer. The answer is 3/8. Now, that was a lot of work for a problem. So how about using this binomial theorem thing that they say? Well, it works really nice. It says, what's the probability that she makes 1 of 3? Well, then that means we're going to do n in our case right here. This is our n, this is our r, right? Because we want to know how many times you can make 1 out of 3. And so this is how the formula works, really super cool. You do 3C1, you do NCR. Then you talk about the probability that she makes it. So it was a 50% chance that she made it, so a half. And we do that to however many we want her to make, in this case 1. And then we do the probability that she doesn't make it, which was also a half. Sometimes that'll be different, right? Like a multiple choice test, you would do a quarter and 3/4. A quarter that you get it right and 3/4 of a chance that you get it wrong if there's 4 answers. And according to this outcome, she would have to miss 2, right? And that will take care of the probability. If you see what that is, 3C1 is 3, and a half to the first is a half, and a half to the second is a fourth. And so that's going to be 3 times an eighth, which is 3/8. And you can see we get the exact same probability using binomial probability because she's either going to make it or miss. Now, not always will this P and Q values be the same. It was just that she was 50-50 in this. And remember, there can only be 2 outcomes. Those have to be the 2 outcomes. One's going to be your successful probability, one's your non-successful probability. That's just another way of doing it. And so here's the last one I'm going to talk about. What's the probability she will make at least 1 free throw? I guess I lied. It's not the last one. Tree diagram, again, super helpful because think about what at least 1 means. At least 1 free throw means that she makes 1 of 3, or 2 of 3, or 3 of 3. And so again, I could go up and count all of those ways, or I can just use binomial probability again. So to make 1 of 3, it would be 3C1. The chance she makes it is a half to the first, and the chance she misses is a half, and she would do that twice. Or it would be 3C2. This is her making 2 shots. The chance she makes it is a half, and she'd have to do that twice. She would miss half the time, and she would have to do that once. Plus 3C2, half is that she makes it 3 times, and a half would be that she misses 0 times. And if you add up those probabilities, you should be golden. Like this was 3/8. Now, what is this? This is also going to be, now I have to do calculator 3, and this is a fourth, and this is a half. So what is that? That's also looks like 3/8. And then this last one is going to be 1. Oh wait, why did I do 3? This should be 3C3. That would be 1, and then this would be an eighth, and this would be 1 because anything to 0 power is 1. So what do you have? You have 3/8 plus 3/8 plus 1/8. What is that? 7/8 chance that she will at least make 1. In fact, what's the only way she can't make 1 is if she misses, and we see that right here on my tree diagram that she's got a 1/8 chance of missing all 3, and so therefore 7/8 would make sense. All right, let me ask you a question, and we'll do that last one, and we'll be finished for the night. All right, now let's do example 3. You make 4 trips to a drawbridge, and there's a 1 in 5 chance that the drawbridge is raised when you arrive. So that means there's a 4/5 chance that the drawbridge is down. What's the probability it'll be down for at least 3 of your trips? So again, here's that fancy word, at least. That means 3 trips it's down, or 4 trips it's down, or all 5 trips it is down. So we're going to have 3 different problems. Well, here goes the 3 trips, right? So it's going to be 5C3. The chance that it's down is 4/5, and that's going to happen 3 times. The chance that it's up is 1/5, and that's going to happen 2 times. And if you figure out what that is, that will be the probability that it is down for exactly 3 trips. Now we're going to add that to the chance that it's 4 trips. So I will do 5C4. Again, the probability is still 4/5 4 times, but now 1/5 only 1 time. And then the least likely probability that the fact that you pull up and that the drawbridge is down all 5 times. So the 1/5 chance that it's up, not going to happen. All right, add all that together. Now, this one's a little trickier, so I'm going to go to Sheila, have virtual Sheila do this problem for me, and I'm going to be good. So how am I going to enter this in my calculator? I guess I can make a bigger screen so you can see it. All right, so I'm going to hit 5, math, over to probability, NCR 3. So there's 5C3, and I'm going to multiply that, so parenthesis, you know what? I don't know. I don't think it should matter, but I'm going to put times. The parenthesis was 4/5. There's your 4 divided by 5. We're going to raise that to the third power. And then I'm going to go times. Oh, I don't want it up there. So let's move right arrow times what the probability that doesn't happen 1/5. I guess this would have been nicer too to use decimal for a change. 1/5, and that's got to happen the other 2 times. So the second power. And so there you can see the probability, right? And then I can just second enter, we'll copy it over, and I can just change the numbers that I need to change. This has got to be 1. Then I got to go all the way over here to make this a 4. And don't forget that that's got to be 5C4. Don't know if that was any better or not, but boom, there's that probability. So you can see there's already a 60% chance. And then the last one, hope it stays on the screen. Second enter, we're doing 0 here. Oops, not 10. Don't you dare do 10. So you got to be a little careful. So there's the 0. 4/5 would be to the 5th, and 5C5, which is actually just 1. So probably not very entertaining there. And there it is, a 32%. Oh, I guess it was less likely that it would be down 3 times. Interesting. So you can see a 20% chance, a 40% chance, and about a 33% chance. So say a 97% chance that 3 out of your 5 trips you will at least see the drawbridge down. So very likely. So you would again add those up. So let's call it 20, 41, and 33. I would want you to be more exact, but I'm not going to remember. 20, 41, and 33, I think I said. So I would like, maybe 3, 4 decimals would be a little better. 5, 6, 7, 8, 9. And what is that? 3 plus 1 is 4. 94, or a 94% chance. That is pretty stinking awesome. Ken, can you be a little more accurate than that? I'd really appreciate it. All right. Have a great day. Stay happy. And I'll see you tomorrow.